Hello, class. Today we're going to answer one big question. Is music just math? Shout out to the comment that requested this video. Listen, and I know what you're thinking. Devin, how could music just be math? I love music and I hate math. And while I'm at it, Devin, you kind of stink like a big pair of cheeks. Hear me out. I felt the same way when I found out that music was written with math. So this video is going to answer the question, is it just math? Is all music just frickin' math? But before we get into it, why don't you click the subscribe button? It would make my heart tingle. And like the video while you're at it. Give it a little kiss. Here we go. So let's talk about all the different maths. Let's start with the simple stuff you can count in your head. Time signatures. So this is, just counting that has to do with rhythm. The bottom number tells us what length of note we'll be counting in, and the top number tells us how many of those notes are in one measure. Most songs are in 4/4, which means you count along in fours. More specifically, we're counting with quarter notes up to 4 times in a measure. There's some other weird time signatures, though, that are pretty hard to count if you're, stupid. Just kidding. I have a hard time counting these too. Like 6/8. 6/8 is when we count with eighth notes, and there are 6 of those eighth notes in a measure. So yeah, time signatures, kind of scary, not that bad. Brings us to our next math. Note lengths. So there's a bunch of different lengths of notes. We got the whole notes, half notes, quarter notes, eighth notes, 16th notes. You get the idea. To get to those shorter notes, you have to use frickin' division, but it's easy division because they're easy little numbers. Divide the whole notes by 2, you get half notes. Divide the half notes by 2, you get quarter notes. Divide the quarter notes by 2, you get eighth notes. These names also refer to how many notes you can fit in a bar. So one whole note takes up the whole bar. Half note takes up half the bar. So for example, if we're talking about a song that's in 4/4, one bar is 4 clicks of that metronome. Half note takes up half the bar, so 2 clicks of the metronome, and a quarter note would take up a quarter of the bar, so 1 click. Kind of easy. The notes get shorter, not really that scary. Let's move on. Intervals. That's impressive, actually. I didn't even look at it. Intervals describe the relationship between 2 notes. Any 2 notes. I don't give up. We have to use addition as the math for this one. The name of the interval has 2 parts, the number and the type. Let's start with the number. Intervals are measured in steps or semitones. A semitone is equal to a half step, which basically means if notes are a semitone away, they're like right next to each other. And I mean right next to each other. Like, I don't mean how C is next to D, I mean how B is next to C. So if you want to make specific harmonies, you have to do some counting. You also count the intervals between notes to build major or minor chords. Major chords have 4 semitones between the first 2 notes, and minor chords have 3 semitones between the first 2 notes. But sometimes the names of these intervals get a little annoying. Take the perfect fourth, for example. You would think, oh, perfect fourth, it's perfect. 4 semitones freaking away from each other. Wrong! It's 5, but it's a perfect fourth. Whose idea was that? And don't even get me started on the perfect fifth, because the perfect fifth, it can't be 5. Because 5 semitones is the perfect fourth. You know how many the perfect fifth is? 7. Anyway, some intervals sound better than others, or at least in Western music standards. An octave, which is when 2 notes are 12 semitones away from each other, is considered one of the most stable harmonies in music, Western music. So basically that's the space between one C note and the C note directly above it. But why are some intervals more stable than others? Well, I hate to break it to you, but it's because of math. So now that we got all the baby stuff out of the way, let's get a little more in the weeds. Stay with me here. It's actually pretty interesting. Sound frequencies. So this involves fractions. Ooh, fractions. Those are scary. I'm a little startled myself right now. I'm shaking. You can actually make intervals between notes using fractions and math. All sounds are just air wiggling. Am I right, ladies? Me talking right now, the air's just wiggling. And the sound's frequency is basically how slow or fast the air wiggles within a period of time. And it's measured in hertz. Frequencies are what makes sounds higher or lower pitch from each other. So this A note is wiggling at 440 hertz. This A note up here is an A note It's the same note as this one, only it's at a higher pitch, so it wiggles at twice the speed, 880 hertz. These A notes are an octave away from each other. 12 big old semitones, baby! So an octave is a 2-to-1 ratio. So when you multiply the frequency of this by 2, you get the frequency of this. Devin, why the hell is that important? No one cares. Well, actually, here's the thing. The simpler the ratio is between two notes, the more consonant those notes sound together, aka the more stable the harmony sounds that those two notes make. And this is a really subjective way of putting it, but in Western music standards, people tend to think that sounds that are consonant are easier on the ears. This is the opposite of dissonance, and dissonance is when two notes sound kind of tense together, kind of like that one time I invited this girl Megan to a concert, and she didn't want to go with me, and I had to keep asking her because no one else. Personally, I love dissonance. But this is the simplest way I can think to explain it. And we get these ratios from the frequencies of the notes. A perfect fifth interval is equal to 3/2, and a perfect fourth is equal to 4/3. Let's take that A note for example again. A equal to 440 hertz. Multiply 440 by 3/2. Let's do it. What do we get? 660 hertz, and I'm not even left-handed. So this is the frequency of the E note that's above the A, which you guessed it, is a perfect fifth interval. Let's tackle the perfect fourth, shall we? So let's use the same A equals 440. Let's multiply the 440 by 4/3, the perfect fourth fraction. What do we get? I'll tell you. That's what we get. 586.66666. We want to simplify it, 586.667. And this is the frequency of the D note that's above the A. Perfect fourth in between each other. But the more complex these fractions get, the more dissonant they sound. A fraction for a tritone interval is 64/45. So, by 64/45, what do we get? We get 625.78, baby. And this is the frequency of the D sharp that's above the A note, which is a tritone. Yay! Perfect fifths and fourths are called perfect because their ratios are so simple. Pretty cool. And this doesn't even apply to every tuning system. We're just talking about standard tuning right now. Isn't that something? And to top it all off, a bunch of the different tuning systems were found through ratios just like this. We could get way more complicated if we want to, but we're not gonna do that. This brings us to the million-dollar question. No. There's a lot of math in music, but music's not just math. Aside from lyrics, obviously. It's just it's a form of creativity. No one gives a about math when they're making a hit song. No one gives a If they wanted to do math, they would go to the medical school down the street. Most people don't think of music as math, and that's because you don't need to think of it as math to have a fun time doing it. You don't need to understand the math behind music to make good music at all. You can make a hit song. Beatles didn't even know how to read music, let alone frickin' sling all this out of their back pocket. So here's the thing. A lot of math in music. It's really cool to know about. The whole frequencies thing blew my mind when I first heard about it. But at the end of the day, is this something that you need to know by heart? No, but it's cool. It's kind of a fun little factoid. So what do you want me to talk about next? Leave a comment. Thanks.